Okay, so let's go ahead and work this, this buoyancy example. And in this problem, we have an object that has a weight or a mass of 100, it's a weight on a balance, and the balance registers 105 grams when it's in air, and then when it's submerged, it registers an apparent mass of 93 grams. So we want to know what the density of this object is. And the density of this object is its mass divided by its volume. Now the mass is what we're given in the problem. Its mass is 105 grams. So we know that. That's given in the problem. But what we don't know is the object's volume. Now, when this object, and so let's kind of draw our little object here. When this object is submerged in water, it displaces a certain volume of water. So the object's volume is also equal to the volume of fluid displaced by the object. And this is going to be more useful for solving this problem than the object's volume, because we can actually use Archimedes' principle when we're talking about the fluid displaced. And we'll see how that comes into play here in a second. Okay, so let's look at a little free body diagram for what's going on to our object here. And so there's some weight of the object pulling down, and that weight is mg. M was 105 grams, and that's 0.105 kilograms. Okay, and that's times g. Okay, so there's mg for the object. And we're told its apparent mass is 93 grams. So that's essentially how much we have to pull up with on our little scale to make it be stationary in the water here. So our scale then is pulling upward with a force of its apparent mass, which is 93 grams, times g. Okay, so that's the weight we pull up with. That's its apparent weight in water. And there's some buoyant force that pushes up as well. Okay, so therefore the buoyant force on our little mass is the difference between these two things. Because if this thing is going to be stationary in water while we're weighing it with our little scale here, well, the buoyant force plus our, whatever our scale force is equal to the actual weight of the object. So therefore, our buoyant force then is this minus that. So it's 0.105 kilograms minus 0.093 kilograms times g. Okay? So that's our calculation of the buoyant force, just based on sort of the dynamics of the problem. But one can also find the buoyant force from Archimedes' principle. Okay? So Archimedes' principle says that the buoyant force is equal to the weight of fluid displaced. Okay? And the weight of the displaced fluid is the density of the fluid times the volume of the fluid times g. Because this is its mass times, so weight is mass times g, and the mass is density times volume. This is an equation we developed in our lecture. Okay, so we can plug that stuff in. The density of the fluid we're submerged in is water, so that's 1,000 kilograms per cubic meter. The volume of the fluid is what we're trying to solve. And then we have g. Okay? So this, then, has to be equal to this. Those two things are equal. That's our buoyant force calculated by two separate methods. Okay? So these are equal to one another. And I'm just going to bring this over to here now. So 0.105 minus 0.093 is 0.012, okay, times g. So those are equal. The g's cancel. And that allows us to calculate the volume, 0.012 divided by 1,000. That gives a volume for your object that is 1.2 times 10 to the minus 5 cubic meters. Okay, so that's really the important step in this problem. Now we can go back up to our density here, and I'm going to erase this. And the density is the mass of our object, which is 0.105 kilograms, divided by the volume of the fluid displaced, which was this. So 1.2 times 10 to the minus 5 cubic meters. And let me do a little more erasing. And that's equal to 8750 kilograms per cubic meter. Okay, so there's our answer. And you can look this up in some table that has lists of densities. This is copper. Okay, so the object is copper then.